gotta mute my stream as soon as it starts. It's waiting. It's waiting. All right. All right. So, I guess I'll run it for like 2 seconds. See what's going on. All right. Yep. I got a mic check. My mic check was good. I didn't hear yours though. We'll see.
I'm on now.
Yep. Okay. Yep, we'll just wait for it to load up and be good. But we are live.
My being famous right now.
Right. Can you hear me?
Right there. So
I mean, I can hear you. We'll see if we can hear you in stream.
no, I'm not famous now.
Okay. Do I have to mute the volume in YouTube, right?
Yeah, once you get onto it, once you find the
Okay.
stream.
Yep, I'm in there.
I'm famous.
Yes, you're famous. Your picture's in there.
Yay! Peyton, you're not famous. Haha, loser. Yeah, I am.
Quiet.
Shh, quiet.
Okay. I don't know why. It's not really coming up.
You know.
5 are watching, though. I mean, that means somebody's on.
Awesome.
Throw out a hey in the chat, folks, if you're in. I don't know why, but on my end, maybe I need to refresh my search. Yeah, there we go. Cool. I'll
Stop,
check
please.
and make sure we're all good.
Stop.
Sorry.
And I think you're good too. I think your mic checks out. Hello, folks. Welcome to another day of Earth Science with Duprez and Astro, live at 11:03. Not quite 11 on the dot. We had some minor technical difficulties, but here we are. So if you're in, say hi in the chat. We're gonna wait just a few moments to get some more people in, and then we'll talk about the dude that is right here. This man, Alfred Wegener. Iced tea, wet the palate. So we had a couple nice days since last time we met. A couple days getting into like the mid 60s. They were gorgeous, but now we are back to the gray skies. Cold.
Yeah.
It was like 45 last night or something like that.
Yeah, it's chilly.
Yeah, super cold. It's not supposed to heat up for like a while. Pretty weird. This would have been a very, very comfortable school weather environment.
Yes, it would have been.
Hopefully next year shakes out to be very similar.
Just gonna say something.
Ooh, 2 watching. Well, perhaps this will be one that people will be watching after the fact.
Maybe.
Oh well, let's just get started then. So,
Yeah.
here we go. The homework that we had sent out was 3 pictures. It was 3 pictures that all had different things you were looking at. The first picture was of just the continents, asking, look at the shapes, is there anything you notice? The second picture had to do with 2 different fossils, the 2 different locations of the same fossil, and it was of a freshwater reptile that could not have crossed the ocean, asking, well, how could this freshwater thing have gotten between South America and Africa? And then the third picture was asking about mountain ranges and where we find these batches of coal deposits. So the idea was, well, there's all these things that don't make sense with how the world looks right now, how the continents are currently arranged. So what gives? What's up with the continents? And that's why we named it that. So that's what we are going to explore a little bit today. And the story starts off with this guy right here, Alfred Wegener, who was a climatologist, was like really, really fascinated with weather, and eventually through just being at the library, back in those days, you couldn't Google everything. He started to find out that he was really interested in fossils. They were just interesting to him, where they were, how they showed up, where you could find them. So he went from just looking at climate and being interested in how the climate has changed on Earth over the past hundreds, thousands of years, to starting to actually piece together that fossils were in some ways kind of linked. He was really interested in particularly looking at all of the deposits of coal, because coal forms in environments where it's usually really hot. You think of like a really like warm swamp. That's like the environment, and we'll show you some pictures of that later, that you get coal to really form, and he was finding them in weird places. And that went with this fossil data, and he started to like piece all this stuff together. And so that's what your homework really was, is looking at some of the things that this guy, this scientist, was piecing together and going, well, what's up with the continents? Why do all these weird little things go on, but they're in such different places? So the idea, all of these different ideas connected, led him to believe that the continents were drifting, that there was a movement across Earth's surface of the continents, and that back in time you could have had them all be connected. And I'm sure you've heard of Pangea before, right? So you've got the GIF here showing that movement and the continuous changing of the locations of all these different continents, which don't really map where the current continents are today. So this was this guy's idea. Alfred Wegener's idea was that continents must be moving, and he called it continental drift, right? They think of drifting like drifting away, right? So like moving slowly, right? This is not a fast process. If you look at the bottom, we're talking hundreds of millions of years for these things to be working. So that's the time scale we're talking about here. So from the first thing that you were looking at, we were looking at the fit of the continents. So, well, a lot of people have said like South America and Africa look like they just kind of click together, and that's not unreasonable. And we'll look at some other information that tells us that that's totally like a thing. But just looking at it, if you take all the continents as we know them today and sort of rearrange them, they totally look like they fit pretty well. Of course, there's some white areas in between, like over here in this pocket with Florida and whatnot, but the border between South America and Africa totally are a pretty good match. So in the responses that a lot of people put, they definitely clicked with this idea that they look almost like, they say like puzzle pieces, that they fit together. If you were to be like building a puzzle of Pangea, most people would take South America and Africa and kind of click them together.
Yeah, that's usually the most obvious one. And then you look at Asia and Antarctica, and you see they kind of fit to the bottom of Africa.
Yeah, and the other interesting thing is that things aren't in the same north-south way. They're pivoted a little bit too. So like if you look at India, instead of being the way it is on the current map, is like on its side. It's drifted not only just like up and down and left and right, but it's also rotated a little bit. So that rotation also plays a role in the locations. Hey, Victor's here. And we have
Ryan.
Ryan's here. Yeah, cool. Howdy, guys. So that brings us to the next piece of information. So remember, this Wegener guy was looking at all sorts of different things. He looked at that puzzle piece part, and he said, okay, they look like they fit. What else could be helping us make our claim that continents have been drifting over time? So, as we had mentioned before, he was interested in fossils after he started to see these strange patterns of where they were coming up and how it could possibly be that you have these weird, or not weird necessarily, but the creatures living in two different areas that today are very, very separate, where if you look, Mesosaurus was the freshwater creature, reptile, that lived in the southern part of South America, southern part of Africa, but again, it's fresh water. You can't take like a freshwater fish and just throw it in the ocean. It'll die. It doesn't like the salt. So how could it live in those two spots unless they were connected? Same thing with Syngnathus. That was kind of like a hybrid between like a dinosaur and a large cat, I guess you could think of. Had like a huge head and sharp pointy teeth. But that couldn't have swum the ocean as it is today either, right? It couldn't fly. So how could it be in these two places unless, again, they were together? The same thing with the other things that you see here, and same thing with plants as well, right? There are fossils of plants, imprints, that they could say that there was this wide band that went all the way across all these different continents, and unless, and it's a little bit more likely, perhaps, that maybe seeds did travel, but it's still really unlikely that the way that it would have traveled makes this like perfect band when you arrange these things together, like the puzzle pieces also fit. So these two things, really started to get him thinking that perhaps the continents were in different places.
Anybody have any questions so far? Nope. Not seeing anything.
Cool. Well, here we go. Third point. Oh, just kidding. Second point, also evidence that glaciers had been in the area. Again, this Wegener guy, scientist, was really, really interested in climates. So one of the other things that he pieced together with these other two things, where the fossils were lining up, where you had the actual fit, where they look like they click together, there was also these striations of glaciers, which you can see with these arrows, that all lined up looking like they should be coming out from a single point. So if you recall from the last time we talked about glaciers, when a glacier is moving, when it's blobbing outwards, it drags some of those boulders underneath it, and it grinds the bedrock that's underneath. And so by looking at where all these lines are scratched to, you can get a good picture of where it was coming from. So if you look at these arrows, it looks like it was spreading out sort of from this center part of like the picture, like this part right here of Antarctica. So it looked like it was blobbing out from some point around here, spreading outwards over all these places. And again, it's all, if you connect it, making one large circle based on where they found all this glacier evidence. I think it's cool too that they show in the top right where everything sits today, right? You can see here it's totally in different positions. A plant fossil was discovered in Antarctica, meaning that Antarctica was in a warmer place once. We're getting to that. But yes, that is definitely true. So that does bring us to the coal that they found in Antarctica, and we mentioned that coal is forming in an area like this with peat moss. So think about it. If you think about Antarctica, does this type of picture come to mind? Absolutely not. Far too cold, snow and ice. It does not have these kind of like warm, swampy areas with all this peat that just kind of collects and lets things fall into it so it can get fossilized. So the climate had to be different in Antarctica, whether the entire Earth was a different climate or if Antarctica was somewhere else, closer to the equator where something like this could happen.
Right, and both of those, what Mr. Duprez just said about the Earth climate being different or Antarctica being in a different place, are different things to think about. Both possibilities.
So Wegener, unfortunately, did not ever get to figure out why these things had moved, but he on an expedition to go look at more of the climate data up in the north, he eventually ended up freezing, where he is currently buried under most likely about 150 feet of snow and ice that has accumulated in Greenland. So this was a picture they had, you know, a cross and things back in the day when he was buried, but he did not ever actually get to figure out the rest of his idea. That was, you know, why is this stuff moving? So he had the idea of like, okay, the continents moved, they were in a different position, but he never got to fully say like, okay, because this. And that is something we're going to get into next week, because we eventually did find the why. But there are a few other things that we found in between figuring out the why and the foundation he laid down, which actually helped his argument. So one of them has to do with the Mid-Atlantic Ridge, which was something we talked about when we saw the ocean. So we were looking at features in the ocean, right? We were talking about the continental shelf, you got the slope going down, you've got the abyssal plains, and then in the middle of the abyssal plains you had this ridge, this underwater mountain range where there was this volcanic activity. And if you look, it cuts right in between in the same pattern and the same shape as South America and Africa's borders with each other if you put them together. So that formation right there is actually where these things broke apart. So you can see it's also happening in Iceland, and it's not breaking apart any day this week, but the Mid-Atlantic Ridge actually does cut through, and there is a measurable difference in the two plates that meet there, which was something Wegener didn't know. He had no idea about these plates and this movement, but they are moving apart from each other. So that's what this rifting is that the plates will move apart, new material comes up and makes this mountain range. So that ridge right there, that is something that was found post-World War II. They started to have like sonar and detection, looking for the U-boats and looking for underwater mines. And so they found this Mid-Atlantic Ridge, and they started to, you know, get video. Whoa! Oh, there's a weird noise. They started to get like video of it and start to explore it. So this was somewhere around, I want to say like the 50s, that they actually found out about the Mid-Atlantic Ridge. Also, Wegener had died early. I forget if it's the late 1800s or early 1900s. I think it was the early 19. You guys can also Google that. But this was definitely far after his death that they started to find the ridge. So that goes along with this idea, point 4, of seafloor spreading. So we had the ridge itself, which was what led them to start looking at what was going on with the seafloor, and that did let them see, I guess this is kind of a combination with the last slide, that there was some sort of displacement and movement going on with the seafloor. And one of the big things that helps us to understand that was actually the next point, which is the magnetic striping of the seafloor. So they were able to, through a series of testing of the ocean, once we got better technology, see that there was a very, very strange thing going on with how magnets work down there. The seafloor is made of a particular rock that has a magnetic property. So it, if you think about a magnet, right, a magnet has like a plus minus or like a north-south. The ocean floor, since it is made of this semi-magnetic material, is going to show a stamp of which way points north and which way points south. Funny enough, every thousands or a couple of thousand years, every few thousand years, it flips. So you've got it going from north going up and south going down to the opposite. And so what you see in the seafloor is actually these bands showing timestamps, or showing when these flips had occurred, as this material is constantly flowing outwards. So if you look at the picture, it starts off as all in the same direction, and over time there was a flip in our pole of the Earth, which is a predictable thing. It happens on a cycle. So you could see that that yellow part breaks away from the middle, and the new stuff coming up has that flipped orientation. So if the yellow was north is up and south is down, then the red in this picture would be that south is up and north is down, which is kind of weird to think about, but that is what happens when the entire magnet pole shifts. So it took account of that, and then after another, a couple thousand years, it flipped back. And that's why here, where you've got the new material coming up with this magma again, you can see that the yellow is once again there, where north is north and south is south. So this phenomenon in the bottom of the ocean shows that not only was the ridge a continuous process, right, that this spreading was a thing that continuously happened, but also they knew that, it happened over a long period of time. It wasn't like a new thing that was continuous.
Right. One thing to note is that the new material that's coming up will always be in the center. And as it starts to move out, then you see on both sides of the ridge, you see the same pattern.
Right. So it goes, right, yellow, red, yellow, and then yellow, red, yellow at the bottom, right? It's opposite. Or it's mirrored, I should say. But what's cool about this is that this is an imprint showing like that there are polar cycles where the pole shifts, which is just kind of cool. Like just thinking about our current magnetism, like how it could change. It's a very odd phenomenon. But also like this does add to Wegener's idea that things do move. Things are constantly being pushed or moved by something. So this seafloor spreading and this proof that it is a continuous process shows, well, if South America and Africa were next to each other and this rift started there where you've got this new magma coming through, it makes sense that over time it would slowly be pushed apart a little bit and a little bit and a little bit more so that it was going away from each other. So this is really like just showing that the process of being pushed apart could totally happen with this continuous like conveyor belt of material pushing outwards. And that brings us to, we'll skip over this, but basically this is just talking about the pattern of if it's one way here, then it flips, and it's the same on both sides. And here you can see the time scale too. So what is that? To get from the center to the end of the first section was 700,000 years, and then you've got a wait, that's not quite timed right. Oh wait, that was just a lot of material. Yeah, then it was 900,000 years for this little section. So yeah, this is on a big time scale. It's not like again at any time soon we're going to have this big flip of the magnetic poles. It does take quite a while. And that leads us to the last thing, and that's why I have in my little background here, where is it? This one? No, here we go. Boom. Whoa, there it is. Volcano. Because the volcanoes and earthquakes that do occur on Earth all line up with boundaries, these lines where we eventually figured out that there were these plates underneath, and that does show us a good amount of, again, why they occur there, because there is magma, there's volcanic activity at these boundaries, as we saw with the mid-ocean ridge, and that does help us understand that these are different pieces and they could move in relation to each other. So just another piece that they eventually figured out as to like why things could move, right? Why would continents move if it was all one solid piece? That wouldn't make sense. So if there are plates that can move in relation to each other, then the continents could certainly look like they are moving. Or just literally move, yeah. So I think that's basically the end of what we wanted to get through today. Just talking about some of the ideas of, why are continents perhaps moving. We still haven't answered the thing that Wegener was looking for, though. Why? Why are there these plates that move? Why are there volcanoes and earthquakes necessarily at these things? How did they get there? What was the thing driving all of this? And that's what we will do next week. But to piggyback off of what we just did, we do have an assignment that we're going to post for you probably pretty soon. You can check probably by 12. But it's all about kind of what we just did here, looking at the different maps and matching up fossils, matching up the different things we talked about. So log in the classroom, take a look.
Absolutely. You want to keep in mind the stuff that we just talked about, the pictures that you looked at the other day, and, has you thinking a little more about like why the continents are the way they are and were they together once before.
Yep. So are there any questions before we bid you adieu? Oh yes. Also, happy Cinco de Mayo late. Hope you got to celebrate a little bit. Back to volcanoes.
It doesn't look like there are any questions.
All right. Well, folks, if you didn't catch this live, make sure that if you have any questions, you can always email us. We usually post out about what we're doing in Google Classroom, but we're always open if you have any concerns. And also, don't forget we have our office hours. At this point, I should know them off the cuff, but 12:45 to 1:30 are my office hours, and then Astro has hers from 1:30 to 2:15, again through Google Classroom. All right, so I guess that's it.
Yeah. See
Have
you
a good
guys
day,
next
folks.
time.
Yep. Bye-bye.